Hi, welcome to this, our third installment in a series of videos on circular motion. In this video, we continue to take a deeper look at the theoretical aspects of circular motion. Two very important properties of uniform circular motion are angular displacement and angular velocity. If you recall, linear displacement is the change in a particle's position. So here we have a motion diagram with frames being taken at 1 second intervals, and so in a given second we see the particle moving from, say, this position to this one, and so delta x then will give you the magnitude of the displacement. In circular motion we have something similar. Here we have a particle going around in a circle, and we know it's traveling with a constant speed because notice in every interval this particle seems to travel the same distance along this circle. So at this point in time the particle is here, and this angle corresponds with its angular position, and then at this point in time the particle is here and this is its angular position, and the change in this angular position then is what we have here labeled delta theta. Notice the angular displacements are equal, so once again we can conclude that this thing is traveling around with a constant angular speed. So what is angular speed? We're simply going to say that the angular speed is given by, and this will be the symbol, it's not W, it's the Greek letter omega, and it's given by delta theta, which will be our symbol for the angular displacement divided by the time interval, and the unit will be the radians per second. So this is the unit. If you remember, the magnitude of some velocity would be given by the displacement divided by the time, and this was in meters per second. So look at the similarity between these two properties here. Both of them refer to some displacement divided by time, only that here it's linear displacement and here it's angular displacement. Let's suppose we took pictures of another particle moving with constant speed, but these distances are greater. In such a case, you will be able to conclude that the particle is traveling at a greater speed, and so that's what we have here. Here the linear speed is greater, and for this particle, since the angular displacements that correspond with each 1 second interval are all greater, we can also conclude that the angular speed is greater. So the angular speed is simply the angular displacement divided by the time. So make sure you know the difference between linear displacement and angular displacement. Linear displacement is the change in the position. Angular displacement is the change in the angular position. And the unit for angular speed is the radian per second. Here we have an expression that should be very familiar to you. If you have a particle moving with a constant speed in a straight line, then the final position of that particle along the x-axis should be equal to its initial position plus the product of its linear speed and the time interval. Well, for uniform circular motion we have a very similar expression. The final angular position is equal to the initial angular position plus the product of the angular speed and the time interval. Note we don't have any expression for acceleration here because the speed is constant. Likewise here, the angular speed is constant. In future chapters, we will be looking at situations in which the angular speed will be changing, in which case we will need to incorporate something called the angular acceleration. But until then, for right now, we will look at particles moving with uniform circular motion, in which case the angular speed will be constant. Let's take a closer look at our mathematical definition of average angular speed. It's the ratio of the angular displacement to the time taken. Now suppose the particle undergoes one complete revolution. In other words, the angular displacement would be 2 pi. Of course, the time taken for one complete revolution, we're going to call that the period, and we're going to use this symbol. So notice this gives us a very useful ratio, that the angular speed is going to be equal to 2 pi divided by the period. So this is very important, and you have to remember this. Now, another very important relationship that you need to remember is that the period is equal to the reciprocal of the frequency. So for example, if it takes a particle 0.5 seconds to go around once, then how many times can it go around in a second? It can go around 2 times in a second. So if the period is equal to 0.5 of a second, the frequency would be equal to 2 per second. That is 2 cycles per second. So if a particle takes half a second to go around once, then of course it can go around twice in a second. Likewise, if a particle takes, let's say, 1/8 of a second to go around once, then obviously it can go around 8 times a second. Very often, instead of saying second to the -1, the unit hertz is used. So we could also say 8 hertz. So the hertz is the equivalent of 1 over the second. So this is a very important relationship, so make sure you have this memorized. The angular speed is equal to 2 pi divided by the period, or likewise, and this is perhaps the more popular version. Omega is equal to 2 pi f, 2 pi times the frequency. So that's it for this video. Make sure you understand these concepts and do any and all assignments that go along with this video. Until the next one, bye.